Yeah, so sorry for the delay. The problems were a little hard, and I had to take my time with them. There was a bit of procrastination, I will say that, but yeah. So also you might get my outro today. So yeah, you can check that out if you want. Okay. Yeah, so this is the metric topology. Why am I taking so much time here? I have no idea. Yeah, so this is where, all right, yeah, I start. So first we define a metric. So we have a topology and it's a function from x cross x to R, and x is a topology, right? Sorry, x is a set here. We're defining the topology from the metric. So yeah, and the first criteria is d of x comma y is greater than equal to 0, and d of x comma y is equal to 0 if and only if x is equal to y. Second is d of x comma y is equal to d of y comma x. So symmetry. Third is d of x comma y is less than equal to d of x comma z plus d of y comma z. And of course, for all x, y comma z in x, right? So yeah, if a function, a binary operation from x to r satisfies these three properties, then it's a metric, right? And yeah, from these three properties alone, we can do a lot, including differentiation. So it's quite powerful. Okay, we can't do differentiation for that. We need other stuff, but yeah. So yeah, from this we can define the basis elements, which are I'm going to call them balls. They're also called neighborhoods sometimes, but neighborhoods can be confusing because, well, open sets around a point are neighborhoods. So, but you get the motivation behind the terminology then. But yeah, some people call them bases, some people call them balls. There are many names for them. But this is the definition for it, and it depends on the metric. But sometimes it's obvious. It's a set of y such that d of x comma y is less than epsilon, right? And it's precisely these that make up the basis for the metric topology. So we just have to check it's the basis and then we're done, right? Yeah. So yeah, now we have to check that it's the basis. So first of all, we have a lemma that says for every y in so for all y in the ball of x, right? There is a ball of y such that it's completely contained in it. So yeah, uh, in R2 and visualizing metric spaces as balls in R2 is a pretty good idea, but note that when we're proving anything, we have to use only the triangle in. That's all we get to use. So yeah, ultimately, no matter how small it is, we can get a ball that's completely contained. And yes, this delta is precisely so. Yeah, because we're taking the points that are strictly less than epsilon, right, and not equal to epsilon. Well, d of x comma y is going to be less than epsilon. So what? Epsilon minus d of x comma y is going to be greater than 0. And this delta is precisely going to be our neighborhood, right? So that's one lemma. And then from this lemma, we get so the first condition of basis is trivial because for every x we have a ball around it. So so we're selecting the set of all neighborhoods for all epsilon, and then we're getting the metric topology. So because of that, the first condition is trivially satisfied. The second condition requires this lemma, and I'm going to use it. So yeah, let's say B1 intersection B2 is non-empty, right? So Y belongs to it. So because they're both balls, right? I'm just writing them in short, but they're representing the same thing. There's going to be a B Y comma delta that's in B completely contained in B1, right? and b of y comma delta 2, that's completely contained in B2. And you take the minimum of the two, since the smaller one is going to be contained in the larger one due to totality. Is it totality? No, it's transitivity. If you take the smaller of the two, uh, delta is equal to minimum of delta 1 comma delta 2. B of y comma delta 2 is going to be a basis element that's centered around y. So it is a basis element. There's no problem about that. And it's contained in B1, it's in B2, and y belongs to it. So it satisfies the second condition of a basis. And because of that, we have a topology from these balls. So yeah. Okay. A space is metrizable if there is a metric such that we get the same topology. So a topology is metrizable if there is a metric such that it generates the same topology as X. And a metric space is a metrizable space with a metric. So yeah, that's just definitions. Okay, then we're going to prove metrization theorems later. Yeah. Okay, so now we have a completely metric space based definition. It doesn't extend to topological spaces. And that's, yeah. So this is the diameter. So hang on. Okay, so yeah, if for all, so a subset of X is called bounded if for all A and A2 belonging to A, the distance is bounded by some M, and M is a positive real. So yeah, and if it's bounded, and only if it's bounded, then we, and non-empty, sorry, then we can define the diameter of A, which is, yeah, the supremum of two different things in A. Note that if it's a single point, we can still define the diameter because we can just choose A, comma A. So that's also completely fine. So the diameter can be zero, I think. Let me just check. Yeah, it can be zero. So it's based on the metric space because we can have a bounded metric that generates the same topology, and that's what we're going to study now. Yeah. So d bar is defined as the minimum of d of x comma y. So sorry, d bar of x comma y and 1, right? So if it goes too large, we just choose 1 essentially, nothing too much. And we just have to first check it's symmetric, and then we have to check that it's generating the same topology, right? They're both easy. Yeah, let's do that. So the first two are trivially true because they're going. If it's equal to 0, it's going to be less than 1, right? So we're done. It's the same thing. And if it's x is equal to y, then this is going to be equal to 0, and 0 is less than 1. So it's also going to be 0. Same thing with symmetry. If it's 1, then we're fine. If it's not 1, then we're also fine. If it's less than 1, then the same thing extends. So let's verify the triangle inequality. Yeah. So this thing is less than equal to, okay, it's less than equal to 1 for sure, which is less than equal to 2, which is, hang on, should I do it this way? Hmm. Okay, yeah, it's either, okay, let's see. Okay, yeah, so d of x comma y bounded less than d of y comma z plus d of x comma z. So note that it doesn't really matter since I've already proven symmetry, so I can just rearrange them if I want to, right? Hang on. Yeah, so we just have to consider two cases here. Essentially, if even one of them is bigger than one, then this is bigger than one, and this can never be bigger than one because it's the minimum of one and something else. So it's trivially verified. So we consider the other case when They're both less than one. And in that case, if it happens to be bigger than one, it's the same thing. If it's less than one, then what? Then d of x comma y is less than equal to d of y comma z plus d of x comma z. So yeah, if they happen to be greater than one, it's completely fine. If it's less than one, then we have the triangle inequality for this case. So in general, verifying whether something is a metric is quite easy. You just check the definitions, and the first way is usually almost always done. Uh, the Euclidean metric can be tough, but if with the Cauchy-Schwarz inequality, which we'll discuss in the next section, actually, I think it should be easy. So if you know the right inequalities to help you get there, it's also done. Yeah. And to deal with metric spaces, you just think of the right abstraction device. So we're going to discuss a couple here for the uniform metric and so on. But yeah, so visualizing circles in R2 is probably going to help you, make the right proofs because the circles inherently follow the triangle inequality, right? And because they're the locus of all points equidistant. So because of that, you'll be able to visualize everything better and then make the right proof. But yes, triangle inequality is required, and we have a small theorem, and that theorem is quite powerful. The containment lemma, this one. So that alone can get us quite far, and we won't really be going that much further than that. So yeah. Okay, so we have the Euclidean metric and the square metric. So the Euclidean metric is when the sum of squares essentially, pretty much something like that. So we have the norm, and then from that we have d of x comma y, which is just norm of x minus y. So it's defined in the book. And for the square metric, we just take the supremum over. Is it bounded here? It's not. Yeah, we just take the supremum or max over a finite set. It's fine either way. Over yeah, yeah. So these lead to squares and these lead to circles, and that's so circles are in general the general n-dimensional sphere, right? And these lead to the n-dimensional cuboid if you want to generalize it further. And yeah, essentially, since inside a circle there's always a square, and inside a square there's always a circle, we're going to eventually prove that they generate the same topology. So yeah. Okay. So yeah, let's prove that the square metric is a metric. So for all x minus yi, it's going to be for all I, sorry, this is less than rho of x comma z plus rho of y comma z, right? And since we are checking the maximum here, rho of x comma y is also satisfying the same property. And for the other two, if it's equal, then all the coordinates must be equal. So the maximum must be zero, and if the maximum is zero, then all the coordinates are zero. So that's only possible by definition when the coordinates are equal, and therefore the points are equal. The entire point is equal. And symmetry, because the modulus doesn't really differentiate. So mod of x minus y is equal to mod of y minus x. So this is precisely why it works. And yeah, the mod just, it stays positive. I think you know what the modulus is, hopefully. And yeah, yeah. So now we have a lemma that we're going to use quite a bit in the exercises. And yeah, I don't really need to prove it. Okay. So the proof does require one step, but otherwise it's just an extension of the most, not the most important theorem, but quite an important theorem of the book, which is 13.3. So yeah. So we have x, the same set, I believe. Yeah, the same set. and we have two topologies induced by the metrics. So we have D and D prime and tau prime. And tau is finer. Is it tau prime or tau? Yeah, tau prime is finer than tau if and only if, yeah, for all x and x, uh, for all epsilon greater than 0, so yeah, it's similar to the epsilon delta definition, and you can kind of call it that, but for topologies, B of delta of x, so yeah. Some people write n delta x also, so that's another notation. But yeah, here I'm going to stick to the book's notation here. So delta d prime is a subset of b d x comma epsilon. And yeah, we're going to use theorem 13.3 to help to prove it. So this implies that there exists b such that x for all x and x, b is a subset of b prime and subset of b, right? You must remember that. So from that and combining with the fact that for all neighborhoods, for all points, we can get a neighborhood that's small enough that's centered around it. We can get a neighborhood centered at x, and that's going to be contained. Yeah, I'm just explaining the proof in the book. You can read the proof for more details. And for the reverse, well, yeah, so we have the same. That is, yeah, so the same thing which is contained here is exactly the thing we need for all x, right? So we're getting the reverse statement handed to us directly. So this is the non-trivial integration, right? Okay. And this theorem alone is going to help us prove the fineness and non-fineness about a lot of things. And look at the exercises. The exercises will tell you a lot. Yeah. And that's why I didn't really want to upload the video without uploading the exercises at the same time. So hopefully they're both uploaded at roughly the same time. So yeah. Okay. So to show that the square and the circle are the same, they generate the same topology. Yeah, so I'm going to use, okay, so I'm just going to state a definition that two metrics are called equivalent if there exists C1 and C2 uh, greater than 0, I guess, yeah, such that C1 d prime is of x comma y, yeah, for all x comma y in x is, yeah, less than equal to d of x comma y is less than equal to C2 of d prime x comma y. Yeah. So this is a definition stated in some analysis textbooks. And essentially, yeah, if two metrics are called equivalent, if this is the case. And if you look closely at the proof of the book, we're doing exactly this, but with the square and the Euclidean metric. So yeah. And why are they called equivalent? Because they generate the same topology. And that's because we're trivially achieving the subset criteria with this. This one is giving us that d prime is finer than d, and this one is giving us that d is finer than d prime, or sorry, the topology from the method, right? Because yeah, it acts as our delta essentially, the C2 to an extent. So do I need to add much more to it? Should be fine. Yeah, yeah. There's nothing more I can add. Okay. The product is the same as given by this metric rho. Yeah. Okay. Okay, so in the finite case, the product is the same. That's fine. Okay, so I've given basically all of the tools you need to prove everything. So, you won't really have to check whether something satisfying the triangle inequality. It's usually the easy part. Uh, you have to compare two metrizable topologies. So for that, you use the containment theorem. which is essentially an extension of theorem 13.3. And yeah, so from this point onwards, I'm going to focus more on giving the intuitive picture, and the details of the proofs are pretty much there. Yeah. Okay. So you know what the product topology looks like. It's basis elements, and you just cross them, right? So I u, right, from I is equal to 1 to n. So the product and the box topology are the same in the finite case, right? And these are the exact same as the Euclidean or the square metric topology, and that's because, well, you have any product of open sets, you have a basis element contained in them, and inside them, you can take the epsilon to be, so you have an epsilon gap for all of them, right? You can take the smallest of them all for each x, and for that, yeah, so you just take the minimum of them all, and then you get a product basis element so you get a square metric basis element that's contained in the product slash box topology. And for the other case, it's actually easier because if it's the square metric, then you take the basis element where it's epsilon throughout, and in fact that is an open set in the product topology, so we're done. So yeah, okay. So essentially, you take the basis elements. In one case, they are open sets. In the other case, uh, the square metric can be contained inside of the open sets. And if you have a containment, then by extensions of theorem 13.3, so you can have one for open sets too, and use that, and then yeah. So sometimes you just need to prove that there exists a basis element contained in it, right? And yeah, this basis element sometimes ends up being the open set as well. So yeah. Okay, so then we try to generalize the Euclidean metric to the infinite dimensional space, and we're going to discuss that in the exercises. And for the square metric, it forms the uniform topology, and yeah. So you can visualize the uniform topology as you have a band of x. So you have okay. So you have R omega, right, which is the set of all functions from R to sorry from Z plus to R, set of all functions, right? So yeah, you have a different coordinates essentially, and yeah. So at every single point, you have an epsilon band around it, and that's basically the uniform topology, right? That's the way to visualize it, and it will be much better long term to just use the correct abstraction devices. So things that essentially behave exactly as you would expect them, and yeah, you can just use that to make your proofs. So with the right visualization technique, you can prove it correctly. Like, yeah, so, circles in R2, right? Okay. So, so yeah, for the uniform topology, you visualize them as bands around it. And we're going to explore this intuition better in question 6 of this exercises, right? Yeah. So the exercises covers a lot more intuition. This is mostly just giving you an exposure to how the proof works, right? Okay, so we have the uniform metric, which is the supremo of the bar. So it cannot exceed one. There is also that. And yeah, now let's prove that the uniform. Okay, so in terms of fineness, the box topology is the finest of them all. And the box, uniform, product. So I'll show this, and then in the case when J is infinite, the index set, we're also going to explore how they all can be definite. So if it's infinite, we can also take that plus, and that's exactly what we're going to work with. Yeah. So how do we work with this? Let's see. So we haven't yet discussed how the product metric can be written that way. So Yeah, okay. So let's take any basis element here. So a basis element is going to be not the entire space R at finitely many stages. So, right. And at R, it's going to be something else. Sorry, at the other coordinates, it's going to be R. So we take any point here, and we only concern ourselves with these, right? So because these points are finite, we have a basis element around all of them, right? So we're going to have epsilon1 and epsilon1 band around that each coordinate for all x. And we just take the minimum of them all, and that's going to be a uniform band. So we got essentially a basis element, which is so what do these look like? We're going to explore that in more detail, but essentially think of them as a band at each coordinate. And because epsilon is the minimum of them all, it's going to be contained in all of them. So yeah, the uniform topology is finer than the product topology, and the box one is for the box one, where yeah, you take any band around it, and that's basically an open set, right? Why is that? That's because yeah, it's the definition, right? So it's supposed to be an open set, yeah. So any open set you take, that's going to contain a band, right? It's going to contain this kind of basis element, and yeah, this basis element is a open set and is an open set in the box topology because it's the product of open sets. That's the basis of the box plot. I think I'm explaining a bit too much here. Yeah, I think yeah. So the book, to be safe, it halved it, but you don't quite need to do that. And so the uniform topology is defined through a metric, so it's metrizable, right? But the product topology is also metrizable, and for that we've even defined the metric. The book has it. So to show that this is the case, let's see. Yeah, sorry, it's xi. Yeah, xi, yi. So to the way to visualize it is that we have a finite product of open coordinates, right? So what if we had a tail that goes finitely, and then the other tail is completely infinite? So sorry, the tail is infinite, and the complement of the tail is finite, right? That's kind of what this metric handles, and it's important that this is bounded because otherwise the metric wouldn't work. This 1 by I needs to go small enough from the I increasing to infinity. And that's what the boundedness comes in to help for. So yeah, let's take an open neighborhood here. So any open set here is going to contain a basis, right? X comma epsilon. So we're defining this metric and we're showing that this metric is having the same topology as the product. Yeah. So note that it's not the same topology as the Euclidean metric because it's not even defined yet for the infinite R omega. So in the finite case, they're all the same. There's no problem. But in the infinite case, a lot can go mess itself up. All will be discussed in the exercise. So yeah, we have an epsilon band around here, and what would that look like? That would look like essentially, so epsilon is greater than di upon x comma y by sorry, yeah, by I, right? For all I. And note that there is a one n such that 1 by n is less than epsilon. So we don't really have to care beyond that point because it's going to be less than 1 by n. So before that, we have to look at what it behaves like. But note that they're basically finite, so it ends up being an open set. So before this 1 by n, it's going to be a finite amount of basis elements essentially because it's going to be less than epsilon, and that's precisely what we need. That has a correspondence with the product. And if you take any open set, then it's the same thing goes backwards. So you have, let's say, a couple bands at some points, and it's the whole space at some place. Doesn't matter. You just take a point and you have a basis element around it. And you can do that because of this metric. So yeah, that's essentially what the book is proving. And I hope I covered all the ideas, but yeah, I really don't want to cover what the book is doing. And to show it's a metric, yeah, it's just going case by case essentially. It's the same proof as the square metric. Yeah. So yeah, then it uses an open set and then contained the basis element is contained in the open set. So it's the same proof. Yep. Okay. I know I didn't cover it in that much detail here, but most of the insight is in the exercises, like some earlier sections. This is not really a theory portion. Like it shouldn't have much theory. So you know what a metric is, you know what some topologies behave like, and the product is identical to this metric topology, and that's why the product topology is metrizable. And yeah, oh well, time to do the exercise now.